And welcome to this tutorial on thermography and photovoltaic systems with Johan Piro. He'll be joining us here in a moment, but first, a few announcements. If you have any questions about today's topic, or if you need to contact us directly, please feel free to reach out to the Infrared Training Center. You can call us at 1-866-872-4647 or reach us via email at info@infraredtraining.com. The Infrared Training Center website is where you'll also find free tutorials as well as our complete global training schedule for certification classes. This includes AS&T-based levels 1, 2, and 3, as well as ISO-based Category 1 courses that are now available. Head to infraredtraining.com to learn more. While you're online, be sure to get social with the Infrared Training Center. Follow us on X, Facebook, Instagram, and LinkedIn, where you'll find helpful tips, thermal imaging best practices, and much more. Be sure to also check out Thermography Talk, now available on Apple Podcasts, where we feature these tutorials so you can learn while on the go. The Infrared Training Center also runs a number of special training offers throughout the year. So if you're looking to get certified, there's never been a better time. To learn more about these, please feel free to give us a call, send us an email, or visit the Infrared Training Center online at infraredtraining.com. So with that, let's bring in Johan Piro. He manages a large portion of our training in Europe, including Germany, Austria, and Switzerland. Today he's going to discuss using thermal imaging to inspect PV arrays, including all the systems that thermographers will encounter with this application. Hey Johan, great to see you. How you been?
Hey Matt, I'm fine. And how are you?
I'm doing really well. Thank you for being on. For those that haven't met you yet, what's your background? Let's just start off with some introductions here. How long have you been with the Infrared Training Center?
Yeah, okay. Thanks for having me, Matt, today. I've been with the Infrared Training Center since April 2019, so already 5.5 years now, almost 6. I'm the manager, which is responsible for Germany, Austria, Switzerland. And since last year, I've also been responsible for the Czech Republic, Poland, and Slovakia. My job is basically to conduct trainings myself. We have many external instructors doing trainings for us as well. I also do the scheduling, organization of trainings, handling of materials, content management, the business part. All of this is my role at the Infrared Training Center.
Oh, great. This is great. Well, great to have you on here. I know you brought a presentation. This is doing infrared on PV installations. What's today's presentation going to be about?
Well, yeah, as you said, it's about thermography on photovoltaic installations, or PV. That's what we're going to talk about today. We'll have a look at the different types of modules, types of PV installations, and also see how we can use infrared cameras to actually inspect those installations and modules and all the components which are involved.
Perfect. Let's start off by discussing some of the basics of solar radiation and how the science behind all of this works.
Yeah, let's have a look at it. Of course, what we are trying to do with PV installations is to capture the radiation that comes from sun. So if we look at the source, at the sun, I will not read out these numbers. They are huge. If it corresponds to, the radiation that strikes Earth corresponds to 170 million nuclear power plants. So you can imagine that that's quite a lot. But the important part is, of course, how much arrives on Earth, how much of that radiation strikes Earth. And as the sun is not a disk, it is actually a globe. We have to first simplify it a bit and imagine Earth would be a disk. And there's a so-called solar constant. And this number describes how much radiation from the sun arrives at a certain surface of Earth. Now we know it is not a disk, it is a globe, which is inclined at a certain angle. This number, the solar constant, is only true at the equator and at a perpendicular position of the sun. So the further north you are on Earth, the less radiation strikes even the same size of surface. As I said, the angle of Earth is slightly inclined. And also it has its changing position over the year. So what we have to bear in mind always, it's not always the same radiation from sun that arrives, strikes Earth over the whole time of the year. And of course, that's how we get the seasons: winter, spring, autumn, summer, and of course, day and night. This is what we always have to bear in mind.
So what about the different types of installations? For those that might be new to this particular application, let's talk about that a little bit more. What are these installations that we're going to be running into with inspecting with thermal imaging?
Mm-hmm. Yeah, well, there are three kinds or types of installations. We have the first type is the so-called off-grid, which means that it's self-sufficient, so it's isolated, it's not connected to any external power distribution network. It could be somewhere on your garden house maybe, so you have a solar generator and maybe a battery, and you're just powering some devices. The lawnmower, for example, this would be a typical off-grid installation. So you only produce the electricity for yourself. The next type that we know is the so-called mixed type of installation. So you're producing the energy for your household, for example, and you can also feed this power into the public distribution network. This is called mixed. And then the third type would be export only. So you have a solar generator, a PV module, with which you produce energy and you only feed it into the power distribution network. That would be the so-called export only type of installation. Looking at the components that we have in a PV installation, which are connected to a power distribution network, you do have the solar generator. That's the PV module, the panels. Since those panels create DC, so electricity in DC, it has to be converted into AC so that we can use it for our typical electrical devices. So you need a DC fuse. You also need a DC circuit breaker. You need a converter or inverter, and then you normally have an export meter, because if you export it or feed it into the public network, and you get paid for it, so you have to measure it. That's why you need a meter. And then this electricity is exported or fed into the public network. Looking at the components of the solar generator or the PV module or PV panel, we do have the photovoltaic cells. That's the smallest unit in those panels. And of course, you have the complete component, the complete solar module or panel. Speaking of the different types of cells, we have commonly three types of cells. The first one is the polycrystalline. Then we have the monocrystalline and the thin film cells. Like always, everything has its advantages and disadvantages. It depends on the efficiency. The efficiency of the monocrystallines is the highest, whereas with the polycrystalline, it's the medium. It is also always a question of the price. How much do you have to pay to buy such a cell, or let's say a panel? The lowest or the cheapest ones are the amorphous thin film cells. They have a flexible structure, so you can bend them a little bit, while the others have a very firm structure. As I said, they're cheaper, but they don't have such a high efficiency, so you don't get so much money and power out of it. And you're looking for the best compromise between power, efficiency, and price. I wonder if you've ever come across the term MPPT tracker or MPPTs. Let me just explain in a simple sentence what they do. Those are actually components that monitor. That's why they're called trackers. They track the efficiency of a PV panel. So they're always looking at the maximum output, but depending on the temperature of the module, and then of course the output. This is what those MPPTs are made for. Well, let's have a look at the different types of circuitry of solar modules. Basically, you probably know this from any kind of electrical connections. You have parallel connections and serial connections. With a parallel connection, what you get is an increase of the current at the same voltage, and with the serial connection, it's vice versa. So you have an increase of voltage at the same current. So what we're trying to achieve is the best compromise between the two. So oftentimes you find a mixture of parallel and series connection, and that gives you the most efficient voltage and current values that you can achieve with a PV module or solar generator.
So Johan, how about the characteristics of a solar panel and the environmental conditions that we're dealing with here? Can you please talk about that a little bit more?
If we speak about bigger PV installations that you can find along highways here in Germany, for example, what you do need for that is a relatively high voltage output for the export and the feed into the public network. So what they use for this sort of installation is serial connections of many cells in so-called strings. The problem with the strings can be that the total resistance of one string is defined by its single highest electrical resistance. And the single high resistance can be caused by different kinds of issues or problems. So it could be a degradation of electrical contacts by corrosion, by mechanical wear, thermal stress, for example, shading, like a tree standing beside the installation, or cloud shading a module, or stain on the surface, like from birds, for example, or sand and dust. Whatever kind of staining you may have. Might also be due to cell breakage, so that cells can of course break. And this all might lead to a decrease or even the outage of a whole string. So what we do have to look at with our infrared cameras is exactly these kinds of issues. Because if those cells are affected by these problems, they can heat up. And remember, heat, infrared, there's a certain relation between the two things. So we're looking at those installations with our infrared cameras in order to prevent damages or to recognize if they are not as efficient as they should actually be. Yeah, you also asked me about the environmental conditions that we should use. Of course, you cannot do thermographic inspections on PV panels at night. I mean, the reason should be clear. So what you do need is a minimum solar radiation, and we generally recommend 600 watts per square meter at the solar generator. Or let's say cloudiness, which is also important, should be a maximum of 1/4. As always, with all thermographic inspections, you should always be aware of reflections. This is particularly important if we speak about sun reflections, of course. So be aware that you're looking at glass surfaces, which can have mirror-like reflections, leading to false patterns or patterns that you misinterpret. So you could see the cold sky, reflection from the cold sky. And of course, be aware that you might damage your camera if the sun radiation is very strong, even if it's a reflection. So pay attention, please. What do you look at? You look at the front of the module, you look at the back side of the module. If possible, of course, if it's very close together, you can't always do this with a drone. So you might do this manually, walking around the modules. If it is a freestanding installation, which we also call solar farms, then also be aware or look at the connection boxes on the back of the modules. They also are very important to inspect. Speaking about the other technical aspects which are more related to your device, your infrared camera, there is something to say about the geometrical resolution. We do recommend to have a rather high resolution of 640 by 480 pixels because the modules are not always easily accessible. So you might have larger distances, even more so if you're using a drone. So yeah, be aware of the geometrical resolution. And you should also have exchangeable lenses so that you can have a closer look up on an image or have an overview image of the whole installation maybe, or several modules at a time. Thermal resolution is also important to consider. Not so sensitive. It's not so important that the camera is very, very sensitive. So we recommend NETD value of 0.08 Kelvin. That should be enough. Doesn't matter if you use a mid-wave camera or a long-wave camera. In most cases, people use a long-wave camera because they do the job and they are regularly a bit cheaper than mid-wave cameras. The measurement range, of course, it's okay if it's between -40 degrees and +120. It shouldn't get colder. It shouldn't get hotter on a PV module. Otherwise, you have a bigger problem and you don't need an infrared camera anymore anyway. Looking at the emissivity of the modules, there is glass involved. So on the surface of most of the modules, we have a glass material, which is reflective, but not to a very high degree. Glass can have an emissivity value of up to 0.85, which is rather high. Nevertheless, you do have anti-reflective films on the surface. For the visual spectrum, they are anti-reflective. And they may also have a rougher surface, which raises the emissivity. Speaking about fault criteria, so the question, when is an over temperature a problem, or when can it just be monitored? That's what we call the fault criteria. There are different opinions depending on who you ask. Some say that a delta T, so an over temperature of more than 5 Kelvin, is already a problem. This is what installers say, insurance companies and the owners, which are looking at efficiency. If you ask institutes like Fraunhofer Institute in Germany, they say that an over temperature is only a problem if it's more than 10 or 15 Kelvin. And if you ask the module suppliers, they will say, well, an over temperature of 20 or 30 degrees is not really a problem. That's normal. So it depends on who you ask. If we speak about the imaging, so how do you display the images? How do you record the images? Mostly we use color palettes with a lower contrast, because normally an infrared image showing a PV panel already has a rather good contrast. As always, it's down to the user, but in most cases, it's okay to have a lower contrast color palette.
So Johan, I know we have a number of examples coming up here in a moment, but before we get to that, I want to ask you about additional measurements that you might take and equipment that perhaps a thermographer would be using for these types of inspections.
Mm-hmm. Yeah, exactly. You're absolutely right. You need more measurements in order to really evaluate what you have measured or seen with your infrared camera. Speaking of the infrared camera, let's talk about hazards first. So make sure your camera will not be damaged, because if you look from the back of the panels through them, you might look straight into the sun, and that can damage your sensor. So always be aware of that if you do in PV inspections from the back side of the modules. I said you need a certain minimum solar radiation, 600 watts per square meter. So how do you measure that? There are devices to measure that sun radiation. We see the name and an image of that on the next slide. And there's another device that is very often used, which is called the IV curve measurement devices. Again, this is in order to maximize and optimize the power output. So it's a question of the voltage and of course of the amperes, which are measured. So you can measure that with the so-called EV curve measurement device. The device you use in order to measure the solar radiation is the pyranometer, as you can see it here. Those are typical additional measurements you use. The position that you have to take in order to see the PV panels from above, that can be done or realized using a so-called cherry picker, like sort of a crane that you can see here. But more and more often nowadays, of course, drones are being used because they are pre-programmable. So you can program a flight. It will take the pictures automatically. You can adjust the height, and it makes it much more easier, and it's much quicker than moving around the cherry picker or walking by foot, of course. So drones is a very big topic. And remember, we also have a drone course, an SUAS course at the Infrared Training Center.
All right, then finally, let's talk about the faults that you can find, as well as the various types of inspection patterns that a thermographer might run into doing PV inspections. What do we have, Johan?
Yeah, let's have a look at the faults that you may find using an infrared camera looking at PV panels. I mean, depending on, do you hope to find something or not? Depends on who you ask. A thermographer might hope to find something, the owner probably not. But anyway, the faults you may find are, for example, faulty cells or modules, faulty connections between the modules or with the connection boxes. There might be water ingress damaging the modules, or the electrical connections leading to corrosion, for example. You may have delaminations on the modules themselves. You know, there are different layers that can delaminate or even maybe crack. There are the so-called bypass diodes. They are used if one string of a module might fail, so it doesn't make the whole module fail. There are so-called bypass diodes, and you can see if they are activated or if they are faulty. It depends if they are located in the module itself, then you might see them as a so-called hotspot. Or if it's in the connection box, then you see them as a slightly increased temperature. What else might you see? Faults in other electrical components, whatever is involved here, many electrical components, as we do it in the classical electrical thermography, typical faults that you might find like with connectors or inverters, converters. Remember, DC may have up to 600 or even 1000 volts, so that's a very high voltage. As you asked, looking at the different patterns that you might recognize or that you should be able to recognize as a thermographer who does PV inspections. A simple pattern, the first one that we see here in example A, is that the whole module is warmer. I mean, you recognize the warmer here in this image with the yellow cells. Those are the warmer ones. What could be the possible root cause? In this case, it could be the module is not connected, so it's in idle mode. What do? You check if it is connected. You may have a single string which is warmer. That could lead to the bypass diode connecting through, maybe because of shading, or maybe the bypass diode is even broken or faulty, or you may have a short circuit within the module. The example C is a bit more complex or complicated. So you see a heterogeneous pattern, heterogeneous warming of single cells. If it's a fixed pattern noise or a patchwork pattern, this is what it's called. That's what it will look like as an example here. What could this be down to? It could be because of a solar radiation which is too low, under 500 watts per square meter, or maybe the module is in short circuit. Very simple problem that you often run into is that a single cell is warmer because it's maybe broken, it's faulty. It could also be shading, but that's rather unlikely, I would say. It would then be the weakest link. Another example of typical patterns that you may run into, you can see several modules here in example A, which are warmer at the same time. So there might be an issue with the inverter of this section. Maybe it's broken or there's a connection problem between the different modules. It may also be a reflection. So you're seeing a reflection on two modules in this case, and it's not really the module which is warmer. You just see a warm reflection of any sort of object which is in a certain position. You may also see not the full cell which is warmer, but only a part of a single cell. That could be because this cell is broken or cracked, or maybe it's a problem with the soldering. And as you can see it in example G here, this is certainly dirt because you see it on the very heterogeneous forms of the warming. So it's a scattered pattern, as we call it. You see sharp edges across the several cells, so they're covering several cells at a time, and that's often stain on the surface of the module, like bird droppings, which is not avoidable, unfortunately, of course. And this leads to a higher absorption and emission, and therefore a higher temperature on the module or on different cells. We've spoken about the sun radiation, so the different solar radiation conditions, and we see some examples here. Images taken with a long wave camera on the left and with a medium wave camera on the bottom, and of course the photo in the middle here. These images have been taken under cloudy sky conditions with a rather high resolution on the long wave camera and with a 55-degree angle lens. And the other IR image has been taken with a medium wave camera, as you can see here, with a 40-degree lens. So you see the difference in the images. The next example, we have also low solar radiations because it's just before sunset. And again, what you can see here on the panels, of course, these are reflections from the sky and from clouds. So the darker parts here that you can see on the long wave camera image, this is the radiation, the reflected radiation from the sky, and the warmer reflection, those are from clouds. Next example is on a sunny winter's day, like today here in Germany would be a perfect example for that. In the early afternoon, so the light is not so strong anymore. The sun is already going down a little bit in the early afternoon, and you can also see the different types of images here. They are a bit more similar now, the long wave image compared to the mid wave image. And you can see it on the photo that the sun is already in a in a much lower position on the early afternoon. Yeah, we've been speaking about reflections as well. Everything you do with an infrared camera, always bear in mind that there might be reflections. If it's sun reflection or a heat reflection from anything else, be aware of it. So reflections is a huge topic as well. You can see that here, if it's a wide angle image, of course, you can have a different type of angle closer to the camera, and you have another angle the further you go away or the further you look away. And then, of course, you also see the different kinds of colors in this rainbow image, representing different types of or different directions where the reflection comes from or the radiation comes from. So another image that we have here of reflections, this angle is very low. So of course, if you are a little bit familiar with thermography, you know that the lower the angle, the lower the emissivity, and the lower the emissivity, the higher the reflectivity. So you see the reflections in a much stronger way, and they also come from a different position as soon as you change the angle with your camera. So you do have warmer reflections, probably up here from clouds, and these are certainly reflections from the colder sky. And what you see down here could be maybe a building or a tree or something else. This is not the right position or the right angle to inspect a PV module or any other kind of object, of course. Those who are familiar with thermography and have learned this maybe in our trainings know this for sure. Another thing to bear in mind, if you compare the two images here, the photo on the bottom left with the infrared camera image, if we look at this cold spot here, where we have this little arrow, this is, of course, a little hole in the sky between the clouds, so to say. You cannot really see this well in the photo, but you see it very clearly with an infrared camera. And this is where the minimum temperature comes from. So the minimum measured temperature here in this, or apparent temperature, we should say, is minus 26. Those who've heard about level and span know what that can cause for the image. So we have to be aware of that. Make sure that the global radiation is as homogeneous as possible. And if you see something very cold or very hot in the image, think of it maybe being a reflection. You can see another reflection here on the roof, on the metal part of the roof here, which is basically a reflection from the tree in front of that building. Okay, I said if you do an inspection of PV modules, you should look at them from the front side and also from the other side, from the back side, at least if it's a farm module. If it's mounted on a roof, of course, then you will certainly not look at it from the back, but if it's a PV module in a farm. And there you can also see on the top left image here, these are definitely, what you can see here, this little part, this is definitely the reflection from the module, which is standing in front of this one. And of course, if you look at the back side of the module, then you can also see connection boxes, and this is always at the same position. This is, of course, not a problem on the cell or on the module. It's simply the connection boxes that you can see here. But this one, the warmer one, this spot here is certainly a heated cell in a module. And you can also see it in the same position, just looking from the other side of the module. Yeah, I've spoken about geometrical resolution before. The further you are away from the panel, the higher the resolution should be. You cannot always get this close. If you can get this close, it's fine. But if you're standing further away, what you do need is a higher geometrical resolution. We recommend 640 by 480. And you should also, as I said, have exchangeable lenses, because if you cannot get physically closer towards your panel, then you should at least try to get optically closer to it by using an angle or a lens with a smaller angle, viewing angle. So what we do see here in this example, if you look at it, it is in a very high detailed image. If you look at the bottom of this panel right here, you can see some heated cells. You might not be able to see this if your camera does not have a good resolution, or if you're standing too far away and maybe don't have the appropriate lens for it. Also, the NETD value, so the sensitivity value, matters in this case. But I mean, if you can present this to your customer and show it, look, there's a problem you have on your PV module here, this matters, of course. Yeah, it's different kind of quality that you can present to your customer. Again, 640 by 480. If you had only half of the resolution, the image would, well, to put it in simple words, be half as good. That really is an important point to consider here. And the further away you are, again, the higher the resolution has to be, or you have to use a lens with a smaller viewing angle. Okay, so we've looked at many farm PV installations. Let's have a look at some more typical examples, like roof panels that you have on private houses normally. They look like this. And of course, you can find the same problems. That's not a different kind of a PV module. You can have the same problems, like in this case, you have heated cells, and not just one, but several ones, but they're all within the same module. You can see that perfectly here. This is a single module, which is sometimes used for traffic signs, for powering them. Of course, what you can see, it's just bird droppings, and bird droppings simply cause shading, and shading leads to an increase of temperature of the module, particularly of the covered cells, of course. Typical example for bird droppings. Another example we have here, which is a very interesting pattern. If you look at this diagonal shape on one of the modules on the bottom left, you cannot really see what it is from the thermal image, but you can see it in the visual image. There's simply a power line on top of that roof, and that is covering or shading one of the PV modules. So that's causing this sort of kind of pattern here. Very particular example. Again, doing PV inspections is just one example, one application for thermography. The principles and basics of thermography apply to PV inspections like for any other kind of inspection or application. So again, taking care of or considering T reflected apparent temperature matters, of course. Angle, everything that has to do with emissivity, all these parameters influence your images and your measurement. This is no different to PV inspections than, let's say, building inspections. So be aware, where are you positioned with your camera? What's the angle? Where does the radiation come from? Is there a changing angle within your image? How does that influence your image and your measurement? This is something that we teach in our trainings in general, not only for PV inspections. Okay, so as a last example, what we're looking at here is the backside of a farm PV module. And what we see is a thermal anomaly at a connection box. You cannot see it very well in the overview image on the top right because we're too far away. So if we get closer or use a lens with a smaller viewing angle, we can see it here. And if we compare this with the photo, we see what component it is. And it is definitely a problem with the connection box. So don't only look at the modules and the cells, but also at all the other components which are involved here that can heat up or cause a problem and a fault and a damage.
Well, that's great. Thanks, Johan. That's lots of great examples. I really appreciate you putting that together for us. I know it's a topic that people have been asking us about, and we haven't done a lot of webinars on these. We just had one recently that gave us a taste of doing PV inspections, but this was very comprehensive. So really appreciate it. Thank you. Really, thank you for your time today.
Yeah, thanks a lot, Matt. It's been very interesting to me to present this to you. We do have PV courses. Whenever you're interested in any sort of infrared training, just look on our website. You will find all the schedules all over the world. Of course, also photovoltaic, but not only. Remember, electrical, building, whatever you're looking at, we've got it in our portfolio.
Remember, if you have any questions on today's topic, please feel free to reach out to the Infrared Training Center directly. Call us at 1-866-872-4647 or reach us via email at info@infraredtraining.com. Our website is where you'll also find other free tutorials on a variety of topics and our complete training schedule. Plus, we also run a number of special training offers throughout the year. To learn more, give us a call or or visit the Infrared Training Center online at infraredtraining.com. Thanks again for watching, and we'll see you online again soon.